Okay, hi everyone. Thanks for coming. Hi to everyone on Zoom, and if you're watching on YouTube, and also if you're watching in person in the lecture theatre, thanks for coming. I'm now going to hand over to Andy, who will introduce our speaker for the day and chair the seminar.
Okay, hi everyone. Good afternoon. Welcome to the seminar. It gives me a very great pleasure to welcome Daniele Brandt from University of Sao Paulo. So Danielle obtained her PhD just last year in 2020, but she's been in paleomagnetism for a lot longer than that. She's been a physicist and technician at the famous lab in Sao Paulo since 2005, and an undergraduate there before that. And during her PhD, she also did an internship at another famous lab up in Scripps, University of California, San Diego, and her interests are in paleomagnetism and temporal variations of Earth's magnetic field, very aligned with what we do here, and I've seen a lot of really nice papers come from Danielle in the last few years, so that's why I wanted to invite her here. So over to you, Danielle. Thanks.
Hi all, I'd like to thank Andy and Caitlin for the invitation to present this seminar, and thanks to the audience. I'm too glad to be here, present my study, and hope you enjoy it. I will talk about part of the research that I did during my PhD at the University of São Paulo and at IGPP Scripps, California, with the financial support of CAPES. This work I did with the orientation of the professors Márcia Ernesto and Kelly Constable. This seminar is about the study of paleosecular variation of the Kiaman Superchron, using analysis of directional distributions of paleomagnetic data. We can assess the geomagnetic field from Earth's past through the magnetic record preserved in rocks. Changes in the behavior of the geomagnetic field through the geological time, for example, in the mean intensity of the field, or changes in the directional variability or frequency of reversals, can indicate changes in properties and morphology of deep Earth. As we go back in time, the paleomagnetic record becomes rare. Thus, statistical models of paleosecular variations are used to study the long-term variability of the geomagnetic field. In this work, we consider the simplest configuration for the mean field, the geocentrically axial dipole. Along the Earth's history, the polarity of the field has changed continuously, intercalating periods of high-frequency reversals and others with practically no changes. Here we have the geological time scale with the geomagnetic polarities, indicated by this column, using black to indicate normal periods and white for reversed. Long-time intervals, comprising tens of millions of years of a single one polarity, define the superchrons. 3 superchrons have been recognized in the Phanerozoic: Moyero, Kiaman, and the Cretaceous normal superchron. The superchrons are known as stable and quiet periods with high intensity of dipolar field and small variability. Recently, several papers have focused on the paleosecular variation behavior during the superchrons. The last one, from Dubrovini and others, evaluated the latitudinal dependence of PSV models and showed that their parameters are not reliable proxies for reversal frequencies. So the main scope of this work is to study the long-term variations observed from directional distributions of the Kiaman Superchron, how they differ from the last 10 million years, and use the giant Gaussian process modeling for interpretation. For studying the paleosecular variation of the geomagnetic field of the Kiaman Superchron using directional distributions, we use as material the paleomagnetic data available. Every paleomagnetic study contains a table with magnetic directions and/or virtual geomagnetic poles that are used to determine the mean paleomagnetic pole, which is often the main result of a study for tectonic applications. The mean paleomagnetic pole removes the paleosecular variation in which we are interested. The magnetization of different sites, geological instants like lava flows, are considered as spot and random readings of the past geomagnetic field. The best target rocks for doing these assumptions are the extrusive rocks, as they cool very fast and record with fidelity the direction of the past geomagnetic field. This variability of the field is measured by statistical parameters as angular dispersion of VGPs or shape and scale of directional distributions. The models commonly used are the statistical models like Model G and the giant Gaussian process type. If we rotate a data set from a single paleomagnetic study with the expected direction to the vertical and use an equal area projection, we can observe how the data is distributed around the average. So we can observe the aspect of the paleosecular variation around the mean field for a geographic site. We can also observe how the data is elongated along the paleomeridian. If we consider that the paleosecular variation have a zonal mode and a symmetric behavior, then we can merge data sets of same latitudes and opposed hemispheres. Here, we can observe a single data set, which is a data set from Permian lavas of Kazakhstan, rotated to the vertical. And all the data sets from paleolatitudes bands from 30 to 40 north and 30 to 40 south merged. When we use this rotation, we also need to consider that each paleomagnetic study or a paleomagnetic pole have its mean corresponding to the gauge field. The models that we considered in this study are the giant Gaussian process type. They are PSP model able to predict directional distributions in any place on Earth. Here we have a 3D plot of simulations of TKO3 model. These points are random vectors that represent the magnetic field at different instants. See how the vectors are distributed around a mean direction with zero inclination at the equator, and how this mean inclination changes up to 92 degrees at the pole, following the gauge model. Here we have the equal area projections of simulations at the same latitudes, 0, 30, 60, and 90. And here we have the equal area projections of rotated simulations, which shows better how the distributions of directions are dispersed or clustered, circular or elongated. So it is not only the mean direction that changes, but also the shape and scale of distributions around the mean. The giant Gaussian process are based on the descriptions of the geomagnetic field by spherical harmonic functions, where the geomagnetic field is the gradient of the magnetic scalar potential. This Gaussian process consists in considering the internal sources of the geomagnetic field represented by the Gaussian coefficients varying under statistical normal distributions. So each Gaussian coefficient have a mean value and a standard deviation sigma. So for building a GGP model, we needed to set the mean Gaussian and the mean Gaussian coefficients and their variances. The simplest mean field is the gauge version, which has only one Gaussian coefficient different from zero, the G10. The simplest mean, the simplified GGP model, as defined by Taux and Kent, have the Gaussian coefficients variances determined from L degree, and all standard deviations are proportional to a constant alpha, using the formulation determined by Constable and Parker. Taux and Kent modified the formulation proposed by Constable and Parker using a beta constant of 3.8 multiplying all variances of antisymmetric families to differentiate them from the symmetric ones. So a unique beta constant used instead of determining independently the first 2 degrees of standard deviations. Then, for a simplified GAD version of GGP, we need only 3 parameters to be determined: the mean G10, alpha, and beta. And if the covariant model is used, the list of correlation proposed by Bono and others is inserted. The orthogonal components of B are linear combinations of the Gaussian coefficients, so the geomagnetic field B varies under 3D Gaussian distribution, where lambda is the inverse of the covariance matrix of B. If we consider a covariant type of model, we need to consider the covariance matrix of the Gaussian coefficients for determining the covariances of B. M is the expected value for the magnetic field from the time averaged field, which is the geomagnetic field described using the mean values of Gaussian coefficients. Since we are interested in unit vectors, we need to use the directional PDF, which is the PDF found by the integration across all values of intensity ρ of the paleomagnetic vectors. These are the PDF for unit vectors using equal area projections of TKO3 model rotated with the expected direction along the vertical direction at the equator and at latitude 25. We can observe how the distribution elongates along the meridian and what is the size of the distribution observing north and south and east and west distributions. So we can determine this measurement using standard deviation along this axis, north and south, that is the standard deviation determined for xn coordinate, and east and west, that is the standard deviation determined for the xe coordinate of equal area projection. We can determine this numerically for a given model and experimentally for a given data set rotated to the vertical. For real data, we need to consider the experimental error that can be assessed by the mean alpha 63 of the directions from the data set. Here we have determinations of the TKO3 from pole to pole for latitude steps of 2 degrees. The purple curves are the numerical determinations from unit vectors PDF, and the symbols are the determinations for 10,000 of synthetic samples drawn from the model. This continuous curve is the standard deviation along north and south that we call sigma n. And the dashed curve is the standard deviation along the east and s that we call sigma e. For the TKO3 model, the sigma n is always higher than the sigma e, which gives the aspect of elongated distributions. And at the poles, they are equal, giving the circular aspect to the distributions. We can use the ratio of the variances E prime as a measurement of how elongated are the distributions. For the measurement of how dispersed the distributions are, we can use the overall variability. And here is the plots of these parameters, of these measurements. These are the predictions of standard deviation east, north, mean values, elongation, and variability for different versions of simplified GGP models, starting from TK03 in black, dashed black, and the red version is the reversed version of the TK03 model, and change the alpha and beta parameters. The resultant shape and scale change with the set of the parameters chosen. The standard deviation north and south and east and west are symmetric to the equator and independently of the polarity. So we can use this type of model for the past, when we very often don't know the polarity and hemisphere. So with the PSV10 database from Cron and others, we evaluated the shape and scale of distributions and fit a new simplified GGP model for the last 10 million years. Here we have the equal area plots for PSV10 sites separated by latitude bins of 10 degrees. The standard deviation north, sigma n, were determined for these groups of directions and are shown as red circles in here. The sigma e is shown as blue stars. For all latitude bins, the sigma n is higher than sigma e, and the results, at least at 70 degrees, follow the same tendency of the prediction of the simplified GGP models. Therefore, the use of latitudinal dependence of sigma e and sigma n seems to be diagnostic and can be used for modeling. Having this positive result for the last 10 million years, we applied this method to the Kiaman period. But the available compilations for Kiaman had a small number of directions per site. This was because the filtering process was restricted to guarantee a good reliability of data. So, for increasing the number of data, we decided to build a database with less restriction, and the filters used are the following. Paleomagnetic studies from igneous rocks only, primary magnetization, age in the Kiaman interval, the Mag code at least 2, exclusion of sedimentary sites. Here is the map of the sampling site of the studies. We also excluded unreliable sites and include only data sets with at least 5 independent sites. Here we have the number of sampling sites per latitude bands, joining North and South Hemisphere. In red, we have the complete igneous Kiaman database, which is available at the MAGIC database. Mean paleomagnetic poles were filtered using mainly the IAGA database, Global Paleomagnetic Database. We also used the MAGIC database and bibliographic search for the recent studies. 91 poles were found. Then 91 tables of declination and inclination were taken from the original publications, resulting in a database with almost 1,500 directions. A total of 6 latitude bins have more than 150 data. Evaluation of whether the dataset distribution sampled the geomagnetic PSV adequately was based on an independent A95 envelope following the Nin and others methodology. In light blue, we see the datasets that were considered as representative of the general PSV behavior of the Kiaman database. We decided to focus our interpretation in extrusive rocks, purple bar, as they can be considered as spot readings of the paleo field. Here we have the equal area plots for extrusive sites separated by latitude beams of 10 degrees. In green results, we have positive paleolatitudes results, and blue are from negative paleolatitudes. The standard deviation north, sigma n, were determined for these groups of directions and are shown as purple circles here. Sigma n are the stars, the purple stars. The last few million years models, TKO3 and BCE19, are shown as black and gray curves. Note that the first beam of latitude 0 to 10, sigma n, is higher and different from sigma e, which describes an elongate distribution. See the elongation E prime here. Seems that at least for this first beam, the PSV of Kiaman is similar to what is found for the last 10 million years. But we can also observe that for both sigmas are lesser than the last 10 million years, showing a smaller PSV. See the overall variability in here. For the other beams of paleolatitudes higher than 10 degrees, all distributions are practically circular in shape and with a small scale of distribution. We try other filtering processes to check if the circular and the small distributions were affected by the type of rock, number of sites, or bad intra-site statistics. And no firm conclusions were found. The circular and the small distributions persist. Given that, we choose to continue with the extrusive results as the best representative for our study and searched for simplified and covariant models that best explain our results. Here we have the plots of Kiaman results, extrusives, of sigma e and elongation and variability. The gray curve is the BCE19 model for the last 10 million years. Purple curve is the simplified GGP model adjusted for the Kiaman results, and the green one is the covariant version. We searched for the models that minimize the square differences between standard deviations data and model. Here we have a table containing the final models for the Kiaman, the simplified and the covariant version. For finding this model, we previously set a mean intensity of G10 based on the average of virtual dipole moment listed in the available paleointensity database. G10 has positive signal as it is from a reversed model of the field. The mean intensity of G10 found for Kiaman is higher than the last million years. But it's important to note that this intensity was obtained without any quality filtering of data. The parameters found by the minimization were the alpha and beta constant. And the alpha constant depends on the previously set G10. See how the alpha constant that multiplies all standard deviation of Gaussian coefficients is comparable to the last million years models. The beta constants are also comparable. A small size of distribution, like our results, could be generated by a strong mean field or by a smaller variability of the field. So if the G10 represents the reality of the Kiaman field, we can affirm that what is really changing in the Kiaman Superchron is the intensity of the mean field and not the variability of the magnetic sources. A high intensity for the mean field with the same size of variances results in a small directional distribution. So for generating a small distribution, we need small relative variability that is given by the ratio of alpha and G10. See how the relative variability is lower for the Kiaman period. Among the tested models, the best model fitted was the covariant type. See the chi-squared and L misfits found for the Kiaman models, indicating that the correlations proposed by Bono and others is also valid for this period. Other observation that seems to persist a long time is the beta constant. This indicated that the relation between symmetric and unsymmetric families variations is not changing in the geological past and seems not to be a proxy for reversals rate. This is similar to the finds of Dubrovin and others using G model for the Cretaceous normal superchron. Therefore, the contrasting parameters found for Kiaman times are the relative variability and the paleointensity. Further work should be done to verify if these parameters found from GGP modeling can be used as proxies for evaluating the geomagnetic changes along the geological time. It is important to note that the models fitted for the Kiaman Superchron describe poorly the data results. The distributions of directions are approximately circular, concentrate, and essentially invariant for latitudes higher than 10. If the circular behavior is resultant of underestimated error, then the PSV of Kiaman Superchron is more suppressed than this. So for summarizing my presentation, we present a new type of PSV statistic based on the standard deviation sigma E and sigma N of equal area coordinates of distributions of directions rotated to the vertical. For a zonal model with gauge mean, the latitude dependence of this standard deviation is symmetric with respect to the equator and independent of polarity, which allows us to try this model for the geological past when the polarity and/or hemisphere are very often unknown. The use of the latitudinal dependence of sigma E and sigma N seems to be diagnostic and can be used for further modeling. A new database of paleomagnetic directions of igneous Kiaman sites was presented. The distributions of Kiaman directions reveal low paleosecular variation, and GGP models, simplified and covariant, were found for this period. So thank you.
Thank you very much, Danielle. Virtual clapping symbols coming in there. So nice talk, and I have some questions, but I will give other people a chance to come in with questions first. So if anyone would like to, you can put your hand up or unmute and speak. Okay, I'm not seeing any other questions, so I'll start with one of mine. So I just want to check that I'm understanding this right, because I think yeah, it's kind of important finding you've made here about the Kiaman. So you're saying essentially that the G10, the axial bar magnet of the magnetic field, so that was stronger than the last 10 million years, but effectively everything else, all the non-dipole field, was indistinguishable. Is that correct?
Indistinguishable. Oh, the variances.
Yeah.
So the variability.
Yes.
Yeah. Well, the thing that we can measure using this approach is essentially the relative variability, because we needed to set up a size for the dipole, for the mean dipole. So this size was set as like a mean value of virtual dipole moments, but it should be anything else. Because when we do this procedure of looking only to the directional distribution, we are looking to the distribution, the relative distribution. So if we consider that this mean dipole that is higher than the last 10 million years is representative of the Kiaman, of this superchron, then, for example, let's compare covariant model with covariant model here, only to have this this reference here. So if we have a G10 that is higher, and we have variances of the Gaussian coefficients, so the variances of the whole families of Gaussian coefficients of an internal source, similar to the last few million years. So we can say that the small distribution is caused by a strong field. So this small distribution can be caused by a stronger field, or can be caused by the diminishing of the variation of the magnetic components. So if we consider this is true, we can say that they don't change too much in size in terms of the other components of the magnetic field.
So that's a fascinating claim then, because it's almost suggests kind of a source separation in the it might be consistent with the claim of a source separation. Are you familiar with like what Ken Hoffman's argued for before, that that the dipole basically is derived from a deeper part of the core, and everything else is dominated by stuff near the surface of the core. So effectively that gives you a mechanism for varying the dipole by making convection more vigorous in the deep core, whilst the upper core stuff just does its own thing, possibly dependent on what the mantle has dictated as its boundary conditions and so on. Yeah, I wonder, have you thought about that? What could be causing this sort of almost independence of these two different parts?
I don't know this study. I need to study this. I don't know if I can go further with this interpretation, because I set up this mean value, and it's for part intensity results. They are so rare, and I stay like I don't know if the intensity is too high, and I'm not sure about this affirmation. I think we need we need there are other studies in other times that we have more polyintensity determinations and see if this proxy is okay. So I didn't think more further as you did.
Yeah, sure. I mean, we've just finished analysis of all the paleo intensities in the current database and giving them QPI scores for their reliability. And say you have to go to really quite strict reliability criteria to be able to say to not be able to see this that the Kiaman is really quite strong. So it does look, it's not, of course we'd like more and better data for that period, but I'd say it's a reasonably robust finding that the Kiaman was associated with a strong field. But I wonder if you could, you could turn this on its head and see if you looked at a time period where the field was weaker, where there's low paleo intensity proliferate, like the Jurassic or something, and do the same sort of analysis and see if again you could explain what you see in terms of these relative direction dispersions, just in terms of having the dipole different while keeping, while everything else more or less stays the same.
Yeah, this is a very good idea.
Okay. Do we have any other questions from anyone? I can keep going for a while, otherwise.
Anthony has his hand up.
Oh, okay. So let's do that. Go ahead, Anthony.
Yeah, hi. Thanks for the talk. It might be a really generic question, but can this method be used on like superchrons that maybe with like a lower field intensity, or on more data, or I don't know, like can it be used easily on another superchrons? Sorry.
I don't know if I understood the question. The question is if we can use this methodology for other periods?
Yeah. Yeah, exactly. Yeah.
Yeah, we need to always think that we need to use simplified models to look to the past, because we need to consider a mean field for determining the latitudes where the continents were when they recorded the geomagnetic field. So we needed to set up a mean field before starting, and so we need to we need to take care only with this, and then we can do. And also we needed to consider that for interval of time for tens of millions of years, the geomagnetic field, we are looking to the overall behavior of the geomagnetic field along a long interval of time, like tens of millions of years. So like this superchron, we did this work, and the superchron has 60 million years of duration. So we are considering that the rocks that recorded the field along this size of period has approximately the same behavior. So there are some assumptions that we need to do, but we can apply. As we were using, we use the Model G for the past.
Okay, thank you.
I don't know if I answered.
Yeah, you answered well here. Thank you.
Thank you for your question.
I was wondering what the next steps are in your research. Like, are there extra complexities that you can add in the model in the next steps?
Well, the next steps. We need to, one thing that we should do for example, Kiaman, and is look into these circular distributions, because circular distributions are common when we are talking about experimental errors. So if I don't know if the we don't know if the experimental errors are well determined for every data that was considered in this work. So one thing that we should do for improve this this analysis is considering other sources of experimental error, like when we are determining the characteristic components. We have now a procedure to propagate the experimental errors, so we can do that. We can apply this modeling for other periods of time. And one thing that I would like to see if this the relation between symmetric and symmetric families continue being the same, and what we can use as a proxy for studying the variation of the geomagnetic field. And for Kiaman, if we think about the experimental errors and the propagation of the experimental errors, the question that we can open is maybe this paleosecular variation is so small that we are not able to detect. So using the paleomagnetic data, we are able to detect the past paleosecular variation. So this is a question that I have from these results. And this is.
So just to follow up on that, talking about the distribution of the VGPs. So yeah, if they're circular and sorry, distribution of directions, if they're circular as directions, then that would imply that they are elongated as VGPs. Have you looked at that elongation at all to see how severe it is, and if it's pointing in any, are they elongated north-south or?
I don't remember. I think it is, because I think the effect is elongated along the meridian. I think I calculate lots of parameters, measurements of this, but I don't remember the resultant elongation. But of course they are, because they are circular in direction.
Yeah.
Yeah.
Yeah, I wonder if there's a, you know, there's a danger that they're elongated because, I don't know, there's someone removed remagnetization or something that's causing that.
Yeah, it could be, but I think is asymmetric distribution in terms of directions is common when you are looking to experimental errors. So I think it's more near. It's more near we look to this. And for remagnetization, I don't know if it would be so. It's not constant, but so. I forget the name.
Regular, yeah.
Regular is a systematic. Is a systematic appearance. So if you look to other types of filtering process, other type of rocks, all of this point here, but it's about 30 data only. you see that they are circular, and this is systematic. So yeah, I don't think we should have a remagnetization in all data that we are considering here, and we have lots of type of works. Of course, they can have some bad removal of components, but I think I think the result would not be this regular circular distributions, but future work with the best filtering process, considering best quality of data, can answer this question.
Great, thanks. Any other questions from any of our viewers? No, well, in which case I will say thank you again very much, Danielle, for your talk and your time in preparing it. And I'll hand back over to Caitlin now.
Yeah, thanks everyone for coming. I believe Danielle has a seminar to go to at 4, but yeah, if you want to hang around and chat until then, feel free. Yeah, thanks to everyone who's tuned in on YouTube. There's people. Oh, sorry, we've got a question on YouTube. I just saw one come in. Actually, it's not a question. It looks more of a discussion. Maybe you could have a look afterwards. But they say thank you for the presentation on YouTube, and you've got a lot of likes on there as well. So I think they all enjoyed it.
I think it's my family.
Yeah, thanks everyone for